Hello everyone, welcome to our project presentation on ECE 645. My name is Muhammad Mustafizur Rahman and I am partnering with Solomon Bhulla. Our project topics is self-organizing network and its benefits towards the service provider and how they can reduce their burden, right? So in this presentation we'll go through about the SON and the concept of SON and how the traditional network operation is being performed by the service provider and why they need to use SON and what are the features added to the SON and by utilizing those features how the how SON is providing benefit to the service provider. Here we'll see what is SON in detail, right? So SON is a concept introduced by 3GPP and it is an automated platform, right? And it is designed to make the service providers task simpler and faster, to make their planning, configuration, optimization, and healing process in a same platform, right? So as we know that the network element are increasing day by day, and also the technology is getting changed very rapidly. We started with the 2G, then 3G, then LTE, and now we are adding the 5G, right? So managing all those technology by a single service provider without any single platform, it is very difficult. So that's from that need 3GPP actually introduced this SON, the SON feature, right? So it has four basic features. First one is the automatic configuration, and then second one is optimization, and third one is the diagonalization, and then self-healing. Diagonalization and self-healing are combined together. We actually will present here as a single module in our presentation going forward. Here we'll show you how the SON infrastructure looks like. As we told before, SON is a self-learning technology and it learns all the network element and the subscribers location automatically, right? And it configures a new BTS. Whenever a new site is added to the network, it configures very consistently. And whenever configuration is done, it starts monitoring that site with the another sites, and whenever there is an optimization opportunity is needed, it optimizes the network automatically to increase the coverage and quality. And whenever any outage or failure is happening into the network, it also detects those things and it also solves those problems automatically. In this slide, we'll show how the conventional network operation is being done or performed by service provider and why they need SON. Here we see this is the centralized database system, or we can say this is a NMS, network management system, right? And there is a team sitting here called the performance team, and this team is continuously getting the database, getting the historical data, and they monitor the performance on a daily, weekly, or hourly basis, right? And they actually they analyze the performance trend for different parameters, right? Whenever they find any performance degradation, they actually try to identify the root cause and they propose some solution to the optimization team. That optimization team also digs do some dig down the fault, and then decide what kind of solution they will propose. And based on their proposal, that solution will be implemented either in remotely or in a field. And whenever the solution is being implemented, then again we can get the performance data from the database, or the track test team again go to the site to do the track test. So you see here, so everything is happening one after another and all are being done by separate team. So it is very difficult and very time consuming, right? So whenever a fault is happening here and ultimately getting the solution is very difficult. So all has been proposed in a single platform, and that platform is called SON. Here we'll see the SON architecture. There are three types of architecture. We'll see here centralized, distributed, and hybrid system. We'll mostly discuss about the centralized system. Not mostly, basically we'll be selecting the centralized system. Here we'll show you the three stages of SON. First stage is the self configuration, and it is a plug and play system. It can roll out very faster. It is a very consistent system, and it can upgrade and update the software, and it can manage the resource very efficiently. The second feature is the self optimization feature, and it optimizes all the radio parameters, including the physical cell ID, and it also updates the neighbor relations automatically. It helps to mitigate the interference with a feature called ICIC. Mobility optimization robustness. Mobility robustness optimization is another module included into the self optimization, and it also helps to do the load balancing. In the self-healing, it is a failure mitigation tool, and it continuously monitor the performance, and it helps to rectify the problem very faster. Here we'll be talking about detail on by on process. First of all, we'll see here the self configuration. So whenever a new unit B is switched on or power on for the first time, it needs to connect to the we call the core network, right? So it needs to connect to the MME service gateway, packet gateway, right? And also it needs the IP address. Once the connectivity has been established, right, then unit B will connect to the NMS system, and after that connection established, it downloads the software, and it downloads the configuration parameter including tag, PLMN ID, global cell ID, physical cell ID, and it creates an the interface between the MME and unit B called the SON interface, and parallelly it will update the neighbor list table so that whenever traffic is in the mobility mode, it can hand over from one side to another side. So those are the things that are happening by the introduction of the self configuration module. We'll see here the self optimization part. So once the basic configuration has been done, right, so as per the 3GPP, self optimization will do the PCI optimization part. It will add the PCI first of all in the self configuration. Will add the PCI, but in this optimization steps it will actually optimize. We'll see in our next slides how this is happening and why this is very important. And it also does the ANR, as I told you, the ICIC, MRO, and the MLB features, right? Now we'll be focusing mostly on the PCI part, right? So this is a very important thing, and this start with the self configuration. And first of all, we'll learn about what is PCI, right? So we know that in LT there are 504 physical cell ID numbers called PCI, and those 504 PCIs has been grouped into three different cell identity group. Those grouped are called the secondary synchronization signals, and each group has 168 numbers from 0 to 167, and another group is called the primary synchronization number. There are three numbers, 0, 1, and 2, and the PCI is a combination of the secondary SSS and the PSS. Here is the formula we can use: PCI equal to 3 times SSS plus PSS, right? And PCI module, or the SON module, actually basically works based on the PSS. We'll see how it works, right? So going to the next slide, we'll see here, right? So there are two major things we need to know in terms of the physical cell ID perspective. So one is the PCI confusion, and another is the PCI collision, right? So what is PCI confusion? So whenever a new site is added, right, so the SON assigned a PCI to the site. Actually, SON assigned PCI to the east of the individual sector, right? So say for example, right, so this is our site having the PCI number 3, and this is their neighbor sites, right? So what we can see here, this is the neighbor of this site, and this is also the neighbor of that site, but there are two neighbor sites having the same PCI. So if any if two neighbors having the same PCI, then that there is a conflict is happening, right? And that conflict is called the PCI confusion. Then what is collision? Collision is actually more important than PCI confusion. Collision is if one side is having the same PCI of the neighbor side, then that is called the PCI collision, right? So self-optimization identify those PCI confusion and also the PCI collision problem, and then rectify rectify those problems. Otherwise, it can be very, there will be a lot of call drop, there will be a lot of interference, right? So this is the very important and basic things, right? And that part is very important, because if we do not know that, it takes even hours and hours to do that manually, but self-optimization can do it very quickly, right? So we'll see in the next slide how it is, how it is solved the problem, right? So what happened here? PCI, I told you, right, is that every sector is assigned a separate PCI, right? But assigning a separate different PCI is not the solution. Solution is what is the mod 3 or the PSS value for that PCI, right? Mod 3 is the PCI divided by 3. If PCI divided by 3 equal to 0, there is nothing left, then this is called the mod 3 equal to 0. If PCI divided by 3 equal to remainder is 1, then this is called mod 3 equal to 1. If the remainder is 2, then mod 3 equal to 2. Normally, traditional network, they assign mod 3, if the mod 3 equal to 0, or we can say this is the PSS, right? Mod 3 or PSS, right? So PSS 0 is for sector 1, PSS 1 is for sector 2, and PSS 3 is for sector 3. If we find any orientation of the PCI is like that way, that each sector has having a different mod 3 or different PSS, then you can see this is very good. We don't need to do anything, right? Unless the neighboring have some different conflict or something like that. We'll see in later. In this figure, we can see that the alpha sector having the mod 0 and the gamma sector is also having the mod 0. That means the two sector having the same PSS, right? So in that case, there is a PCI conflict, right? So in that case, the self-optimization identify this problem, right? And then assign any of this sector, right, with a different PCI, so that it has to be mod 1, mod 2, right? Here is 0, here is 1, here is 2. This is another problem. This is one of the side. This is another neighbor side. That side is having the different mod for the different sector. This side is also having the different mod or PSS for the different sector. But if you see that these two sectors are facing each other, but they are facing each other, that means they are the neighbor. If the neighbor is having the same mod or same PSS, that means this is also a PSS conflict. PCI, self-optimization tools also identify this kind of problem and also rectify and propose a new PCI having the different mod, right? So it does not it does not create any kind of confusion here. Here is an example here, pictorially, we show here. This is our cell A, and this is my neighbor cell, and this is another neighbor cell, right? But these two neighbor cells having the same PCI. In that case, here as we saw, the concept like PCI confusion is created here, and here we saw that this is the right orientation of the mod, but this is the wrong orientation of the mod, right? So here we see the duplicate PSS, and and in this figure we saw that this is a PCI confusion is happening. In that case, actually, it has been rectified by the SON. Is very important feature, right? So this is one of the the theory of operation we're proposing here. So that operations is a index. It measures the index based on the different values of the angles and the distance, high, medium, and low, and based on the the calculations, right? It creates it finds a problem where is the PSS conflict is happening, and based on that it rectifies and it changes the PCI, right? So next slide, I'll briefly discuss about the PCI optimization in 5G. PCI optimization is 5G basically the same as 4G, but the difference is the number of PCI is double than the LTE. In LTE we have the 504 PCI, but in 5G we have the 1008 PCI, but everything is same. We have the same SSSS and primary synchronization signal, right? And the concept is totally same, so everything will be similar for the LT. Next part is the automatic neighbor relation. So Solomon Bulla will cover this next part. I will request Solomon Bulla to go ahead from here.
Thank you, Mohammed. Hello, everyone. This is Salman Vula, and in this slide, we'll be talking about automatic neighbor relations (ANR). So, by now, we all know that handovers are one of the most system and technology-intensive occurrences in wireless cell phone communications. Now that point being made, we will introduce the topic of ANR. So, each and every ENB has a list of detected neighbor cells, and this list is utilized in connection with handovers. Now, updating ANR is a continuous operation that may be more intense during network expansion, but it's still a time-consuming task in numerous networks. The task gets even more cumbersome in cases where we have several layers of cells and when we have several networks to manage. In the case of LTE, another layer of cells is actually added, which increases the complexity, and thereby optimization of neighbor relations ends up becoming even more complex. Due to the size of the neighboring relation tables in radio networks, it is a humongous task to maintain the neighbor relations manually. And therefore, neighbor cell relations are targeted for automation, and ANR is one of the most important features for an SON. In order to explore its full potential, ANR needs to be supported between network equipment from different vendors. Basically, what that means is that the companies who manufacture the cell phone tower equipment need to work with other companies who also manufacture cell phone tower equipment so that they all can manufacture equipment that's compatible with each other. So ANR was therefore one of the first SON functions to be standardized in 3GPP, and it was one of the first SON use cases to be standardized, motivated by possible savings compared to a labor-intensive manual configuration of the neighbor relations parameters. Especially in a rollout, the ANR may decrease the time needed to get LTE networks up and running. This is the main reason actually why, even though the advantage we have over long periods may not be so big, the initial advantages of this feature are very important, at least in the startup phase. Last but not least, it is recommended that ANR should be implemented at ENB rollout in the future, where there is a possibility of applying inter-RAT ANR. It should be included when it becomes available. In this slide, we'll be looking at the ANR procedure. We'll take a look at the simplified call flow chart for ANR. It's pretty self-explanatory. You have the UE, the E node B, and the neighboring E node B culminating in the MME. The MME being the key control node for the LTE access networks, and one of the jobs of the MME is to include idle mode, user equipment paging, and tagging procedures, etc., including retransmissions. In this next slide, we'll be looking at automatic neighbor enhancement and its theory of operation. So automatic neighbor enhancement works in the following order. We have the manual relations where cell relations are created or deleted. We also have the addition or removal of existing cell relations to or from the blacklist, and the addition or removal of existing cell relations to or from the whitelist. So the blacklist being any entities that we do not desire, and the vice versa. Then we have the clean sweep operation, where the deletion of unused relations occurs. And next in line is the location-based intra-frequency relations, where relations are created for both existing and new cells. These are deleted in the event of any sort of feedback failure, if there's a bad feedback coming in. And then we have the PCI conflict resolution, which is the physical cell identifying conflict resolution step, where we detect rather and resolve collision and confusing PCI conflicts. It's also responsible to resolve conflicts through relation blacklisting. We also ignore cells from exception list, which includes cases like cells with missing geographic information, cells that are not operational anymore, or cells which have any sort of special events, which are also known as a do not touch list. This next slide is a continuation of the previous slide's topic. We should know that for each cell, whether it is existing or a new cell, SON creates a list of interfrequency neighbors to add automatically. This list is made up by using geographic location data and the radio propagation distance calculation. Later on, a coverage polygon is created for each and every cell. So the neighbor relation table consists of all the cells in this list. We should also note certain exceptional cases while we are here, and there are basically two of them. And the two are basically: a neighbor is not added if the distance to candidate neighbor exceeds the relation maximum distance for creation, and a neighbor is not added if the number of intra and interfrequency neighbors is limited by maximum intra-relations. If and when we reach such a limit, SON will not add new relations for the anchor cell. Also, in the following three cases, relations are not created. Case 1 being where a cell with a PCI collision, case 2 being where a cell that will cause PCI confusion with an existing neighbor appears in the list of cells to add, and case 3 being where two candidate neighbors that create PCI confusion between themselves appear in the list of cells to add. In this next slide, we will talk about intercell interference coordination, ICIC. The main idea behind ICIC is to coordinate transmissions in different cells in a way where the interference and or the effect of it is reduced. I mean, that's all we care about. We want as much less interference as possible. We achieve this by letting each cell let go some of the spectrum resources like time slots or frequency or power in order to reduce interference. We should keep in mind though that when we give up certain spectrum resources, we also give up some capacity, and the capacity is lost. So the gains that we get by operating in an environment with less interference should compensate more for this loss. So you should get more back than rather lose. So in other words, we can't lose too much capacity. The most important gain that can be achieved by ICIC is the ability to provide a more homogeneous service to users located in different regions of network, especially by improving the cell edge performance. Nature and severity of intercell interference depends on the cell types involved. Here we will consider macro pico, and macro femto cell interference. Macro cells are basically large cells with a radius from a few hundred meters in urban areas to several miles in rural areas. The base stations serving these cells transmit with high powers and are able to handle a large number of users. Pico cells are more or less smaller cells. They are deployed by like Verizon or any other operator to enhance the cell coverage, for example, to indoor areas where outdoor signals do not reach well because you're inside a concrete structure or inside some kind of a bunker of some sort or some kind of military location where things are not going in and out so easily, or to add network capacity in areas with heavy traffic such as an airport or a train station or giant stadium or something like that. Femto cells are very small cells served by a low power cellular base station. Typically they are designed for use in a home or a small business, small location, and they're usually installed by the customer or the end user themselves, but they use an operator's frequency and are connected to the operator's infrastructure. In this next slide, we'll talk about mobility robustness optimization, MRO. MRO encompasses the automated optimization of parameters affecting active mode and idle mode handover, so that we will have very good end user quality and performance while considering possible competing interactions with other SON features like MLB, the mobility load balancing, or the ANR. There's something that we all need to keep in our minds here. It is the fact that when we have incorrect handover parameters, we will have negative user experience and also end up wasting network resources by causing handover ping pongs and other types of failures. We could even have, in rare cases, a radio link failure, which is an extreme case. While handover failures that do not lead to radio link failures are often recoverable and invisible to the end user, radio link failures caused by incorrect handover parameter settings have a combined impact on the end user's experience and network resources. Therefore, the main objective of mobility robustness optimization (MRO) is the reduction of the number of handover-related radio link failures. Additionally, suboptimal configuration of handover parameters may lead to degradation of service performance, even if it does not result in any kind of radio link failure. One of the examples is incorrect setting of handover hysteresis, which may result in excessively delayed handovers to a cell that's being targeted. Therefore, the second objective of MRO is a reduction of the inefficient use of network resources due to unnecessary or avoidable handovers or missed handovers. To solve these kinds of issues, a SON MRO mechanism was introduced for the purpose of detecting unnecessary inter-RAT handovers, RAT being radio access technology. During the handover preparation, the RAT in LTE requests optionally the target RAT to perform user equipment measurements of the source RAT. The measurements start following the successful handover back, and the measurement duration is one of the parameters provided by the source RAT, and there's a maximum of 100 seconds for this time duration. The measurements stop if a new inter-RAT handover takes place during this time interval. If during this time interval the user equipment measurements show that the source RAT quality remains better than a certain threshold, the target RAT will report to the source RAT that the handover could have been avoided. So thereby the source RAT may then take corrective action and just adjust the handover threshold or increase time to trigger setting or other parameters for handovers to the concerned inter-RAT target cell that we are targeting. It should be noted that MRO is not critical for the operation of LTE network today. This is because the networks are usually stable macro networks with low to moderate traffic loads. In this slide, we'll be talking about mobility load balancing (MLB). It is to intelligently spread user traffic across the system's radio resources in order to optimize system capacity while maintaining quality end user experience and performance. Additionally, MLB can be used to shape the system load according to operator policy or to empty lightly loaded cells, which can then be turned off in order to save energy and thereby money. The automation of this minimizes human intervention in the network management and optimization tasks. Support for mobility load balancing consists of one of more of the following functions. The functions being load reporting, load balancing based on handovers, and adaptive handover. Triggering of each of these functions is optional and depends on implementation. You should also note that current implementations of the MLB function are relatively simple. Moving load between cells is basically achieved by adjusting the handover thresholds and hence the position of the cell boundaries, and this can actually affect the handover performance. It should be noted that estimating what load and UE will represent in the new cell is not a straightforward thing. The radio conditions in the new cell will be different from what it was in the original cell, and hence the resources required for a certain capacity will also be different. MLB of idle mode UEs is more difficult than for active mode UEs, and to increase the effectiveness of the MLB function, it will be necessary to develop more advanced algorithms. One potential improvement is to choose which UEs should be moved from one cell to another more carefully. Also, in LTE networks that were newly deployed, the traffic load will be modest, and there will be little need for load balancing between LTE cells and 2G and 3G cells. But as traffic increases, the MLB function also increases. So it is not necessary to implement MLB in the startup phases, but as the load increases, it's a very good idea to implement MLB as the load increases. In this next slide, we'll talk about self-healing SON. Self-healing functionality was not initially identified as a part of the 3GPP SON functionality, but it was taken into consideration later because self-healing SON promised reduced maintenance costs, and that's what people like Verizon and AT&T look for. Self-healing is a collection of SON procedures which detects problems and solves or mitigates the problems to avoid user impact and to significantly reduce maintenance costs. And the two major areas where the self-healing concept could be applied are self-diagnosis, where we create a model to diagnose a problem and learn from past experiences, and we have the self-healing itself, which automatically starts the corrective actions to solve the problem. This whole optimization process could be enhanced in two steps. Using some kind of a diagnosis model based on past experiences, or using self-test results. In the recommendation, three different self-healing SON functions are defined, they being cell outage and self-recovery of network elements and self-healing of board faults. For the time being only, though, cell outage is available to most vendors roadmaps, and the two later will therefore not be described in this paper at this moment. So to sum up this entire presentation, we can see the table in front of us. We have set up a table to highlight some of the main features that are important for our operator concerning SON, being timing of introduction of SON functions, the possible savings, and the coordination between SON functions. In this table, we are given our view of important properties of current SON functions. Clearly, the self-configuration part of SON are mature and should be included at rollout, in the rollout phase, while most of the self-optimization and self-healing processes and algorithms are not that important to include at rollout and can be set into operation a few years after rollout if and when the traffic load increases. When it comes to possible savings and performance improvements, we have only classified according to high, medium, and low, since actual percentages will depend on several other factors which will not be discussed in this presentation. Thank you for watching.